Okay, so our numbers are few right now. Maybe there's some people in the testing center that are coming out soon, hopefully, but it's time to get started. So first off, a reminder that the first stage of the written report assignment is due on Wednesday. That's the day that you're supposed to switch with your classmate. And then there's the peer review form on Learning Suite that you will download and use to evaluate your classmate's report. So make sure you have selected somebody to trade with. If you don't have an even number of people, 3 people can trade, that works fine. But just make sure you have someone or a group of students to trade papers with so that you're reading someone else's paper and doing a peer review. And so we won't do that inside of class, we'll do that outside of class on Wednesday, but we'll trade those papers on Wednesday to make sure that we all have plenty of time to read through the paper and fill out the peer review form and turn those in on Monday. So today we're going to start chapter 12. Unlike our most recent chapters that have focused on classes of molecules, this chapter focuses on types of reactions, oxidations and reductions. So we're going to see a variety of different types of molecules undergoing oxidations and reductions. We'll focus today on mostly the reducing aspect of it, learning about reducing agents, learning about the hydrogenation of alkenes and some applications, as well as different ways of reducing alkynes. So first off, in order to understand oxidation and reduction, we need to define them. And they're defined somewhat differently than in general chemistry. Instead of focusing on loss or gaining of electrons, what we focus on is the increase or decrease in carbon heteroatom and or carbon hydrogen bonds. So if we are increasing the number of carbon heteroatom bonds, and that's what Z is an abbreviation for, in most cases they will be carbon oxygen bonds, but it could be carbon nitrogen or carbon halogen bonds in some cases. So increasing the number of carbon heteroatom bonds or decreasing the number of carbon hydrogen bonds. That's classified as an oxidation. Sometimes both of these happen in an oxidation reaction. Sometimes it's just one of them. But either way, it's considered an oxidation. And then reduction is just the opposite. Decreasing carbon heteroatom bonds and or increasing carbon hydrogen bonds. Okay? So we have this helpful figure from the book that shows the relationships between different kinds of compounds containing carbon oxygen bonds. And we see as we go from left to right, we are performing oxidations. The first one, methane to methanol, is not a very common one. That is one that is being worked on industrially, but in labs, the ones that we'll see would be alcohols to aldehydes, aldehydes to carboxylic acids. But you see as we go from left to right, we're both increasing carbon-oxygen bonds and decreasing carbon-hydrogen bonds. You'll also see this O in brackets. That's shorthand for oxidation. That's not reaction conditions, but that's just shorthand indicating that that is an oxidation process. And then as we go the other direction, you see we're increasing carbon-hydrogen bonds and decreasing carbon-oxygen bonds. And the H in brackets is a notation we use to show reduction. Some of these it's hard to see that we've actually we've done both. So here we've got, actually these ones are pretty straightforward. We go from 1 to 2 to 3 carbon oxygen bonds, and we go from 3 to 2 to 1 carbon hydrogen bonds. What's a little harder to see is that in each case, when we perform a reduction, so if we were going from right to left, if we were performing a reduction, we're adding H2. We're adding the elements of hydrogen to a molecule, okay? And we don't really see that here because we've also lost a water molecule as we undergo reduction from a carboxylic acid to an aldehyde, okay? So in each reduction, we are adding hydrogen to the molecule. And if we look at the next figure, this is showing oxidations and reductions with hydrocarbons. So here we're just focused on carbon-hydrogen bonds because we don't have any carbon-oxygen bonds. And going from left to right is what you'll see in the lab. We can reduce alkynes to alkenes by adding hydrogen. We can reduce alkenes to alkanes. We can reduce alkynes to alkanes. The oxidations, we don't have ways of accomplishing that in a single step. We can't just pluck hydrogen atoms off of an alkane and turn it into an alkene. That's too difficult. But we do have ways of converting alkenes into alkynes. We've learned that that's just a two-step process, not a one-step process. Okay? So these two figures show us relationships between different classes of compounds and whether it would be an oxidation or a reduction to generate those compounds. Any questions? Okay. So let's talk about types of reducing agents. I've told you that in a reduction reaction, we are adding hydrogen to a molecule. And there are three ways we can do this. Three ways to add hydrogen. Perhaps the simplest is to use hydrogen itself. Okay? We can use hydrogen as a reducing agent, but we can't use it by itself because the activation energies would be prohibitively high. This is the type of reaction that requires a metal catalyst. So anytime we are using hydrogen as a reducing agent, we have to use a metal catalyst. Okay, and we'll talk about that later on today. So the second way we can deliver hydrogen to a molecule is to add the protons and the electrons separately. So if we think about it, H2 is comprised of 2 protons and 2 electrons. So if we have one reagent that's delivering the 2 protons and another reagent that's delivering the 2 electrons, that's a second way that we can accomplish reduction. Okay? And we'll see that later today in class. We can use sodium atoms. Sodium atoms are fantastic at delivering electrons. If you look at sodium's position in the periodic table, you can see that it's practically crying out, begging to give up its electron. Because if it gives up that valence electron, now it has the noble gas configuration. And usually you're used to seeing sodium as a +1 cation because it's very, very stable in that position. If you have a sodium atom that is neutral and has a single unpaired electron, that's really, really good at transferring its electron to anything it comes in contact with. Okay? So we can use sodium atoms to deliver electrons, and then we would need a proton source. And as we'll see later today, you ordinarily wouldn't think of ammonia as a good proton source, but it works really well for this purpose, and we'll see why that is later on in class. Okay? And then our third way of performing a reduction is to use something known as a metal hydride reagent. Okay? There are 2 of them that we're going to learn in class. We have sodium borohydride, and I'll draw the borohydride part first. Okay. So borohydride is a complex anion, BH4 minus, and then we need the sodium cation, sodium borohydride, and we just write the formula. Usually we write the formula as opposed to the Lewis structure, NaBH4. And then we have lithium aluminum hydride, which looks like this. Okay. So these metal hydride reagents, they illustrate a quirk of Lewis structures, of how we draw Lewis structures. Okay? So when we draw these Lewis structures and we assign the electrons to the atoms of the bonds and so forth, we find that we have formal negative charges on the boron and on the aluminum. So one thing we notice from this is something I've told you earlier in class, which is that a negative charge is not equivalent to a lone pair. I've said that when you draw curved arrow mechanisms, you have to use lone pairs because a lone pair and a negative charge are not the same thing. And this illustrates that because borohydride and aluminum hydride have negative charges but no lone pairs. The second thing that's quirky about these molecules is the location of the negative charge. Aluminum is a metal. Let's look in the periodic table. Boron is considered a metalloid. It's on that border between metals and nonmetals. A characteristic of metals is low electronegativity. So metals have less electronegativity than hydrogen. So when we have a metal-hydrogen bond, in which direction is that bond polarized? It's polarized towards the hydrogen. So we have 4 bonds in each of these cases polarized towards hydrogen. So where does the negative charge in those anions reside? It resides on the hydrogens. It does not reside on the boron or the aluminum, even though that's where we draw it. So it's important to know that the negative charge is spread out over those hydrogen atoms. Okay? Now, hydride is the term we use for H-. We've learned about sodium hydride before, a strong base that can be used to make acetylides. It can be used to make alkoxides. So these molecules, they're called metal hydrides, even though they don't have a full-blown negative charge on a hydrogen. They have partial negative charges on hydrogen. And so they react as if they were hydride. Okay, so they deliver, and we'll see how they do this next period on Wednesday. So they're delivering H- to a molecule. And then if you're trying to add H2 and you've added H-, then you have to deliver H+ in a separate step. So whenever you're using sodium borohydride or lithium aluminum hydride in a reduction, then you have to add a proton source. And in most cases, it's water. You would add water in a second step as a proton source to protonate your negatively charged species. Okay? So 3 types of reducing agents. Hydrogen requires a metal catalyst. We add protons and electrons separately, with sodium being an outstanding electron source. And then we have our metal hydride reagents, which serve as a source of H-, but then we have to deliver the proton separately. Question? H- still has a proton. Why do we have to deliver it separately? Because we need 2 protons. Here we're getting 1 proton and 2 electrons, and so we have 1 proton remaining to deliver H2. So that's why we have to do that. Good question. Other questions? Okay, so let's talk about our first reduction, and that will be the hydrogenation of alkenes. So we take an alkene, we react it with hydrogen, and we obtain an alkane. This is a reduction because we're increasing the number of carbon-hydrogen bonds. What other class of reactions does this fit into? This is also an addition reaction. So many, if not most, of our reductions can also be classified as additions because we're replacing pi bonds with sigma bonds. Okay? So this, like most reductions, is going to be thermodynamically favored. We're breaking a carbon-carbon pi bond, a hydrogen-hydrogen sigma bond, which is not that strong, replacing them with 2 carbon-hydrogen sigma bonds, which are quite strong. So this is thermodynamically favored, but the activation energy is prohibitively high. So in order to get this thermodynamically favored reaction to work, we have to use a metal catalyst. So the book tells you you can use palladium, you can use platinum, You can use nickel. All those metals are used. I'm not so sure about platinum, but definitely palladium and nickel are quite flammable. And so they're not used in their pure form. Rather, what you do is you take very fine charcoal particles, very, very, very small charcoal particles, basically carbon dust, and you absorb palladium onto that. And so the most common hydrogenation catalyst is 10% palladium carbon. So you would have a substance that looks like it's a very fine black powder, and about 10% of it is going to be palladium, and the remaining 90% is just carbon. If you do that, it's usually not going to catch on fire, although I have seen it catch on fire before. Hydrogenation reactions are hazardous because the catalyst is flammable, and hydrogen is extremely flammable. Okay, we actually had a fire in my lab this summer where students performing a hydrogenation, and the hydrogen gas coming out of the hydrogen tank spontaneously ignited. So it was kind of scary. Fortunately, there were no serious injuries and the damage was repaired. But you have to be careful when you're performing these reactions with a flammable gas and a flammable catalyst. You have to follow very, very strict safety procedures. So a few details about this. So this catalyst is insoluble. Charcoal doesn't dissolve in anything. And so no matter what you use, your catalyst will not dissolve. So this is referred to as a heterogeneous catalyst. Because you have a heterogeneous reaction mixture. You don't have a homogeneous reaction mixture in this case. So when your catalyst and your reactant are not in solution, then your reaction rate depends on the rate of stirring. So you get variable reaction rates depend on how well you're mixing. So that's less desirable because it's harder to predict how long your reaction will take. But the thing that's more desirable about it is all you have to do is filter your catalyst and you've separated it from your product. So it's very, very easy to remove the catalyst from the reaction mixture. And there are no byproducts in a hydrogenation reaction. All of the atoms in the starting material and the reagent end up in the product. So all you do is you filter, and then you just evaporate your solvent and you have your pure product. So there are benefits and disadvantages to using a heterogeneous catalyst. So some data about hydrogenations. We can take this particular cyclic alkene. We can react it with hydrogen and palladium carbon. And what we will get is a product where our two methyl groups are cis to each other. So we're only going to get the cis isomer. So what kind of addition is this? Yes, it's a syn addition. So hydrogenation reactions proceed by syn addition only. So our mechanism is going to have to explain this. Going to have to be consistent with this. So there's another interesting application of hydrogenation, and that's known as the heat of hydrogenation. So I told you that hydrogenation reactions are thermodynamically favored. That means they're exothermic. That means that heat is given off. So if you perform the reaction inside a calorimeter, you can actually measure the heat that is given off in a hydrogenation. And that can actually help us understand the relative stabilities of alkenes. Question? That is what we're showing right here. This is the hydrogenation of alkenes that we're talking about. And it is going to be always with a metal catalyst and hydrogen gas. So we see here hydrogenation of cis-2-butene and trans-2-butene. The key feature of these two reactions is they both give the same product. They both give butane. And they both give off energy. And if you measure the energy that's given off in the reaction, that'll tell you the difference in energy between the reactants and the products. If the products are the same, then any difference in the amount of energy that's given off is going to be directly related to the difference in energy of the starting materials. So the alkene that is higher in energy, that is less stable, is going to give off more heat in the hydrogenation reaction. And since we know that cis-alkenes are more stable than trans-alkenes, we would expect the cis-alkene to give off more energy, and in fact, that's what happens. In this case, 1 kcal per mole more energy is given off by the less stable cis-2-butene compared to the more stable trans-2-butene. So this is how this was established. This was how these heats of hydrogenation data is how we learned that cis-alkenes are higher in energy than trans-alkenes. Okay, question? The activation energy is probably slightly different, but I suspect it would be comparable. But there probably is a minor difference there. But all we're interested in here is the thermodynamics, knowing the difference in energy between the starting material and the product. Okay, so kind of a neat application. All right, and then another piece of data that will help us, that's important for the mechanism, is the relative rates of different types of alkenes in hydrogenation reactions. And what we find is that less substituted alkenes will react faster. A monosubstituted alkene is going to react faster than a disubstituted alkene, which in turn will react faster than a trisubstituted alkene. And then our most substituted, most hindered alkenes are the ones that are going to react the slowest. Okay? So we're going to propose a mechanism that's consistent with these data, with the syn addition, and with the fact that less substituted alkenes react faster. And it's a different mechanism than what we've seen before, because it does not involve any curved arrows. Reactions with transition metals are a little more complicated than other types of reactions, and some of them do not lend themselves well to curved arrow mechanisms. So this is kind of a cartoon style mechanism. It's the only one we're going to have like this in class. But even in spite of its limitations, it is going to help us understand the hydrogenation reaction and understand the data that I've written on the board. So the role of our catalyst is to serve as a surface to bring our reactants together. So in our first step, the H2 is going to absorb onto the surface of the catalyst. And the way it's going to do that is the hydrogen-hydrogen bond is going to break, and that's going to be replaced by metal hydrogen bonds, palladium hydrogen bonds in most cases, as shown here. Okay? The way the alkene is going to attach to the metal surface is going to be a little bit different. We haven't shown the pi bond breaking. It's more of a Lewis acid, Lewis base complex. Transition metals, most of them have empty d orbitals, and so they are good Lewis acids. And our alkenes are Lewis bases. Those pi electrons of the alkene can donate into empty d orbitals on metals, and you end up with a Lewis acid, Lewis base complex. So this dashed line here is not a covalent bond, but it is an attractive force that is causing the alkene to associate with the surface of the metal. So in these first two steps, we now have our reactants attached to the metal in close proximity with each other. Okay, so that sets us up for step 3. And in step 3, what we're doing is we're breaking the pi bond and replacing it with a carbon-hydrogen sigma bond and a carbon-metal sigma bond. Okay, so what could we classify this step as? Something we learned in our last section of the class, where we break a pi bond and replace it with sigma bonds. Yeah, this is the addition part right here, where we've added a carbon-hydrogen bond and a carbon-metal bond. We've added hydrogen and a metal to our alkene, essentially. Okay? And then in the final step, the metal carbon bond is replaced by a metal hydrogen bond. Okay? And that's a little complicated. We're going to learn chemistry like this at the very, very end of Chem 352M. Okay, so we're not going to go into much detail on this, but we're just replacing, for now we'll just say we're replacing the carbon-metal bond with a carbon-hydrogen bond. Then our product is released from the metal. It's no longer attached to the metal. And so now we can just add more molecules of hydrogen and our alkene and continue with the cycle. Any questions about this mechanism? Yes? There are two of them, and so that's probably the reason, because they're not terribly strong sigma bonds. But I think the fact that there's two of them is what makes it favorable in this case. Yes?
I guess I'm a little confused why them getting kind of stuck to this plate. It seems like their mobility is way down, and so I don't know how they actually. Normally, I picture reactions as things running into each other.
Yes.
And it feels like that can't happen right now.
Well, you'll end up with an alkene in very, very close proximity to a metal hydrogen bond. So that's how it happens, is that they're just close enough together that once they're on the metal surface, they will react. So let's ask ourselves how this mechanism explains the data that we have on the board. How does it explain the syn addition? Okay, Parker? Okay. Exactly. Since the alkene and the hydrogens are all attached to the metal surface, the hydrogen atoms are going to be delivered from the face of the alkene that's facing the metal. Okay, so both hydrogens are going to attach to the alkene from the face that's pointing towards the metal. So that's how we end up with a syn addition. Okay? How does this mechanism explain the fact that less substituted alkenes react faster? Yes, please. Yes, a less substituted alkene will encounter less steric hindrance as it attaches to the surface of the metal, and so therefore will do so more rapidly than a more substituted alkene will. Okay? So even though it's cartoonish, even though it doesn't show curved arrows, it does explain the data that we have for the reaction. Okay? So we've talked about syn addition. There's another element of stereochemistry that we should address. Let's say that we have an alkene looking like this. And we react that alkene with hydrogen and our palladium carbon. This is a chiral alkene. Of course, the alkene is not a stereocenter, but we do have a stereocenter in this molecule. And so the hydrogen can approach either from the top of this double bond, that would give this product, the methyl group would be pointing down if in the product if hydrogen came from the top, or the hydrogen could approach from the bottom of the double bond and give the cis product where the methyl group is pointing up. So would we have a major product in this case? If so, which one would it be and why? Yes. The right one, why? Okay, so what you're saying is that the less hindered face of the alkene is the one that's going to be pointing towards the metal. And so the hydrogen is going to approach that alkene from the less hindered face. In this molecule, the isopropyl group is shielding the top, so the hydrogen will come preferentially from the bottom. It will come faster from the bottom, giving us a major product with our alkyl group cis to each other, and a minor product with our alkyl groups trans to each other. Okay? Yes? We attached one hydrogen to this carbon and one hydrogen to that carbon. So we end up with a CH3 and a CH. Okay? So you might also notice that our minor product is more thermodynamically stable because you can have both of these groups equatorial if they're trans. If they're cis, you always have to have one axial. This is an example of a case where the less stable product is formed faster. I told you earlier on in class we would encounter a few reactions like that. And so in some hydrogenations, the less stable product is actually formed slower, or less stable product is formed faster than the more stable product. Okay, so you have to look at the transition state. The transition state leading to this product will be lower in energy because it has the less hindered face of that double bond pointing towards the metal. Any questions? Parker.
So maybe I missed it, but if you're adding both hydrogens in syn-addition for that first one, how is the group on top coming out of the page with the group on top coming into the page if it's syn-addition?
So it's syn-addition to this alkene, right? So one of the hydrogens, there's no stereochemistry associated with that because it turns into a methyl group. So it's only if it comes from the top or the bottom that impacts this carbon, which becomes a stereocenter in the product. All right, other questions? So a couple other applications of hydrogenation. We have degrees of unsaturation, something we've briefly referred to earlier in the class, and that can be determined from a molecular formula. In this particular sample problem, we have 3 degrees of unsaturation in the molecule C8H12. And if we reduce that molecule with hydrogen in a metal catalyst, the number of equivalents of hydrogen we end up with is going to tell us how many double bonds there are in that molecule. And since degrees of unsaturation can refer to double bonds or rings, any unsaturation that remains would have to come from rings. So in this case, we lost 1 degree of unsaturation. That tells us that in our unknown compound, we had 1 pi bond, and we must have had 2 rings. Okay? In the days before spectroscopy was invented, in the early half of the 1900s, this was common practice in labs to determine structures of molecules. But now that we have spectroscopy, which we'll start learning later this week and both before and after Thanksgiving, these problems have now been relegated to standardized exams. So you won't see them in class, but you do see these sorts of problems on standardized exams. Okay? And then the book also mentions the hydrogenation of carbonyl compounds with a carbon-oxygen double bond. You can reduce a carbon-oxygen double bond with hydrogen in a metal catalyst, but in most cases it is significantly slower than the hydrogenation of carbon-carbon double bonds. So what that means is that you can typically reduce a carbon-carbon double bond without reducing a carbon-oxygen double bond if you're using metal catalyst and hydrogen. There are other ways of reducing carbon-oxygen double bonds that we'll discuss more in 352M. But there's a very common application of industrial application of hydrogenation of alkenes. That comes back to something we learned in chapter 10. We learned about unsaturated fatty acids or oils. They contain cis alkenes in them. If we reduce oils, we convert our unsaturated fatty acids into saturated fatty acids, which we refer to as fats. And here's an example of that. This triacylglycerol has one unsaturated fatty acid in it. And if we treat that with hydrogen and a metal catalyst, in this case it was platinum, we obtain a fully saturated triacylglycerol. The melting point goes up by almost 30 degrees because we have removed the kink in the chain, as you see from these space filling models. And now these chains stack together more efficiently, and we have stronger van der Waals forces. Okay? This is very common in industry. Consumer products, food companies will do this quite frequently. How many of you have looked at a label of some sort of packaged food and seen the term partially hydrogenated vegetable oil? Pretty much everybody has seen that, okay? So vegetable oils are unsaturated, they're oils, and if you reduce those double bonds, you convert the oils into fats. But we also mentioned in chapter 10 that oils are more healthy than fats. Oils are viewed as generally positive for our health, whereas fats are bad for our heart. They raise our bad cholesterol. So why would we do this? Why would we want to do this? There's actually two reasons. Yes? They taste better? I'm actually not certain about the taste, but consumer preference is one of the reasons. How many of you have ever poured oil on your pancakes before? No, nobody wants to pour oil on their pancakes. How many of you have spread margarine on your pancakes? Yeah, quite a few of you have done that, okay? So consumers don't like to pour oil on their pancakes, but margarine is a partially hydrogenated vegetable oil. It's a butter substitute, and people do spread that on their pancakes. So you get a consistency that consumers prefer if you're converting oils to fats. There's another reason, and it's derived from the fact that our unsaturated fatty acids go rancid. Okay, any of you who've stored vegetable oils, many of you have stored olive oil probably for long periods of time, and you find that it goes rancid. It stinks. I would imagine if you tasted it, it tastes horrible too, but it really stinks out when it goes rancid. Earlier, we've learned the vocabulary word allylic, which refers to an sp3 carbon attached to an sp2 carbon. Anytime you have alkenes, internal alkenes, you have allylic carbons, and those allylic carbons are susceptible to oxidation by oxygen in the air. And as we will learn in chapter 15, since that's a radical process, that air oxidation is what makes unsaturated fatty acids or oils go rancid. So if you reduce the number of double bonds, you're reducing the number of allylic hydrogens, and you're reducing the susceptibility of the substance to air oxidation. You're increasing its shelf life. So you get a longer shelf life if you partially hydrogenate or reduce some but not all of the double bonds in your vegetable oils. Okay, so that's a good thing. But there's a bad thing that's not here on the slide, and that is that a side reaction that occurs in hydrogenation is the isomerization of the double bond from cis to trans. And that gives us trans fats. Okay? What do we know about trans fats? They're bad for us. Okay? What's that? Yeah, they will both elevate your bad cholesterol and decrease your good cholesterol. So they're really bad for your heart. And when you perform the partial hydrogenation, you always end up with a small amount of the trans fats. Once the negative health impacts of trans fats were discovered, then food companies invested effort into tweaking the reaction conditions to minimize that isomerization. If you change the catalyst, if you change the pressure of hydrogen, if you change various reaction parameters, you can minimize the production of the trans fats. And they also put effort into separating the trans fats out from the ones that have the cis double bond. So we can minimize those, but they are a byproduct that is produced when we do this partial hydrogenation. Okay? So products such as margarine and Crisco, those are partially hydrogenated vegetable oils. So all of you have used these before. Okay? All right. Let's talk now about reducing alkynes. So we take an alkyne, we react it with hydrogen and palladium carbon. We generate a cis alkene because it is a syn addition. Hydrogen adding to the same face of our alkyne will give us a cis alkene. But I'm going to put this alkene in brackets because we can't isolate it. Because alkenes are also reduced with palladium carbon and other metal catalysts to give alkanes. You might say, wait a minute, can we just use one equivalent of hydrogen? No. If you're using a gas, you cannot measure one equivalent of a gas. It's just impossible. And so whenever you're using a gas as a reagent, you always have an excess of that reagent. So it's impossible to stop at the alkene using palladium carbon as your catalyst. However, we learned in chapter 11 that the pi bonds in alkynes are weaker than the pi bonds in alkenes. So an alkyne should be more reactive, generally in addition reactions, than an alkene. So if we can reduce the activity of our catalyst to the point that we have a catalyst that will only react with alkynes, then we could stop at the cis alkene. And in fact, this can be done. Okay? And it is known as the Lindlar catalyst. Okay? The Lindlar catalyst is a version of palladium carbon, but it's what's referred to as a poisoned catalyst. Okay? We've added things to it to poison it or reduce its activity. And the book tells you what those ingredients are. The specifics aren't that important. You have some, I think it's calcium carbonate, and you have some quinoline, and you throw some lead in. It's almost like the recipe for a witch's brew or something like that. But the important thing is to know the concept that we've added things to palladium carbon to make it less reactive, so it will only react with alkynes and not alkenes. And that allows us to accomplish this reduction, even though we're using excess hydrogen. Okay? So that's how we can reduce an alkyne to a cis alkene. There's an interesting application of alkynes being reduced to alkanes, an illegal application shown on this slide. Have any of you heard of tetrahydrogestrinone or THG before? Okay, good. What have you heard about it? Yes, avoid THG. So if you've done bodybuilding, you may have heard of THG. THG is an anabolic steroid. Anabolic steroids are a class of compounds that will allow you to build muscle mass without adding water weight. This is very useful if you're a bodybuilder, but anabolic steroids come with side effects, very negative side effects. And so they should only be used under the supervision of a physician. The legitimate reasons to use them would be if you had some sort of an injury or some kind of a surgery that caused some of your muscles to atrophy, and then under the care of a doctor, you could take limited amounts of anabolic steroids to help rebuild those muscles that had atrophied. So tetrahydrogestrinone is obtained from the hydrogenation of gestrinone. These alkenes that don't react are more hindered than the alkyne. So some unscrupulous chemist about 20 years ago or so, 20 to 25 years ago, found that you could reduce this alkyne and not touch the alkenes and get tetrahydrogestrinone, where you've added 4 hydrogens to gestrinone. And that turned this female fertility drug, never approved in the US, but used in Europe in some places, into an anabolic steroid. Okay? And so in the 1990s, there was a company called Balco in the San Francisco Bay Area that made this compound under the radar and distributed it to baseball players and to track athletes. who were then using it as a performance-enhancing drug. Okay? Does anyone know the most famous baseball player who took this? Maybe we don't have a lot of baseball fans in the class, or you're too young. Barry Bonds. Have you heard of Barry Bonds before? Okay, Barry Bonds was the home run king, set the home run records. He was taking THG, or tetrahydrogesterone, along with other home run hitters in the late 1990s. So hopefully none of you will be tempted to take anabolic steroids, because you can see the structural resemblance between an anabolic steroid and a molecule that messes with the female sex cycle. And so steroids regulate secondary sex characteristics. And you may have heard that anabolic steroids can cause some unpleasant side effects, such as the growth of breast tissue, the shrinkage of certain male sex sex organs. And so since you're chemistry students, you'll presumably not be tempted to take anabolic steroids. But Barry Bonds and other athletes were. When this was discovered in the early 2000s, there was an anonymous track coach who was mad that competitors of the athletes that they were coaching were using this. And they mailed a sample of it to a drug testing lab and said, athletes are using this as a performance-enhancing substance. And so they identified the molecule first, identified the molecular structure, and then they figured out how to test for it using techniques we'll learn in our next chapter. And many people may not know that track and field and other organizations, governing bodies of sports, will save blood samples of the athletes for years afterwards in case performance-enhancing drugs are discovered after the fact. And so the Olympics, the Tour de France, all these competitions went back and tested a bunch of samples and stripped away medals and prize money from lots of athletes who were found to have been cheating using this molecule. Okay? So that's an unscrupulous, illegal example of hydrogenation. There are many other legal examples. But last thing for today, what if we want to reduce an alkyne and get a transalkene? We can't do that this way. We can't isomerize cis to transalkenes unless we use those metal catalysts. But there's a better way to do it. We can go directly from an alkyne to a transalkene using sodium and ammonia. Okay? And the ammonia is used as a solvent, so we could write it below the arrow if we want in this reaction. So it's liquid ammonia. Ammonia is a gas at room temperature, so these reactions are run at minus 30 degrees. This is an example of our second class of reduction where we're delivering protons and electrons separately. I told you that sodium is very good at donating an electron. And we're going to draw this mechanism slightly differently than the book does. The book shows you a dissociation of sodium atoms into a cation and an electron. And that does happen, but it's not very well suited to drawing curved arrow mechanisms. So we're going to show kind of a simplified version where our sodium atom collides with our alkyne, and in the process of that collision, just transfers its electron to the alkyne. And that's what's referred to as single electron transfer. That's what those three letters stand for. When you transfer an electron to a neutral species, you get an anion, and you also get a radical. So what we have is a species that we refer to as a radical anion. Okay? It has we've broken one of the pi bonds of our alkyne in the process, and we've added, so we now have a radical on one of the carbons that was part of our alkyne, and we have an anion on the other carbon. This anion is very strongly basic. An anion on an sp2 carbon is very basic. So even though ammonia is a very weak acid, we can deprotonate ammonia. We're going to form NH2 minus or amide. We also formed a sodium cation in this process. And so that's going to give us, going over here, and actually this is a methyl group, not an R, because we use butane. That's going to give us a radical intermediate, okay? So we've done a single electron transferred an electron, and then we have done a protonation. And now we're going to do those same two steps over again. We have a second equivalent of sodium that performs a single electron transfer, generating a sodium cation. That's going to convert our radical into an anion. Okay? And then this anion is going to deprotonate another molecule of ammonia, giving us our product. Okay? So it's a four-step mechanism, but it's the same two steps repeated. Single electron transfer followed by protonation with ammonia. A very, very weak acid, but these vinyl anions are very, very strong bases. So why do we get the transalkene? So notice a couple of things. The radical is still sp hybridized because the unpaired electron does not count as a group. So this carbon is sp hybridized. The lone pair does count as a group. So this carbon is sp2 hybridized. And then down here, this carbon goes in the single electron transfer from sp to sp2. When you have a vinyl anion or a lone pair on an sp2 carbon, its position can move. So you can equilibrate between the isomers. So when you transfer an electron here, you have a rapid equilibration between the cis and the trans anions. And of course, the trans is more stable, so it equilibrates to give the trans, and then the trans gets protonated by the ammonia. And that's how we end up with a transalkene. Question?
Why is it like moving around this double bond there?
Say that again?
If there's a double bond, why is it still spinning?
Because the lone pair's position can move. It's actually the lone pair that's moving. So the lone pair and the methyl group are switching places. You're not rotating about the carbon-carbon bond, but the lone pair and the carbon are switching places. That's how it's isomerizing. That was a good question. Any other questions? And then, of course, the alkyne is more reactive to the single electron transfer than the alkene. So once you get the alkene, it just stops there. Okay? And we'll stop there. We got one more reduction we'll talk about on Wednesday, and then we'll go into oxidations. Please make sure that by the end of the day on Wednesday, you've traded papers with one of your classmates.